So do we have, and Phil, are you logged on? Ping, are you gone? Nobody? Okay. Dave, you have to be actively letting people in, right? Is that or
Yes, that is the case.
I see. Yeah, up to 54.
Yeah. Okay, so it caught up quite a bit there in the last few seconds. So
Yeah, everybody's logging. Oh, we'll give a minute. Okay, we probably should get started. So good morning, everyone in Vietnam, and then good evening, those in the US. So let's go ahead and get started. We have a lot of material to cover today. We also have a lab instruction to do. So let's go ahead and look at the pre-assessment, lecture 10, pre-assessment score. So on this pre-assessment, there's 16 questions, so 10 point each. So the average scores is about 12. So that's pretty decent. So
Buck, the screen you've got up is a little bit slow, or a little bit small for anybody that's on a laptop. If it's possible for you to expand the content, there we go.
okay, yeah, my screen's big. Thanks, Dave. Yeah, so this is the total point distribution out of 59 response. Average is about 12 out of 16, so that's pretty good for pre-assessment. So you guys are up to speed on most of these. Okay, so let's go to. Okay, so this is the lecture 10, part 2 replacement. This is the second part of the fourth lecture. So we are in lecture 1. We went on from sanity to DRV. So today we're going to cover the pre-CTS timing optimization. I think that's probably just the topic. I'm not sure. We may be able to get to power and air opt, but we'll see. Okay, so this slide here kind of give you an overview of the time accuracy as you go from placement to route. So in placement, which is where we are, right? There's no clock tree. The only thing we have is the cell that's placed, right? There's the global routes are estimate, and then the only thing we can do is a close setup timing. So there's no clock information, and the detail routes are not in. As you move on to the next stage, CTS, you see there's more data available. You see the clock tree is going to get routed here. So the actual clock tree get calculated, and also which mean that there are clock skew, and you'll learn about those later. And then the only thing here that is estimated now is the detail routings. So once you move from CTS to route, which is where the detail route happens. So detail routing means that all the signal non-clock nets get routed. So here you get all the RC, all the real nets. So the timing is more accurate in post route, right? So here, as you move on, the time actually is more accurate as you go toward the end of flow. Okay, so we're currently in this stage placement. So the RC will be for the nets for the signal nets will be estimated global routed, and there's no clocks. Okay, so in timings, when we're trying to optimize timing, there's a concept of timing groups. So the four basic one. So you have what's called rest to rest. So basically, it's a register to register. This is the timing path between this clock input D to the next flop D is called rest to rest. So it's a register to register. It's called rest to rest path group. And then you have what's called rest to out, which is the timing from a register output Q to the primary output of the design. It's called register out. And then you have interrest is basically primary input to the D flop to the pin of the D pin of the flop. It's called interrest. And then the other path is called into out, basically the logic goes straight to a combinatorial logic to the output. There's no register in between. So these are the primary four. And then you have additional path groups. So when you have the what's called ICG, integrated clock gating cells, and we'll discuss that a little bit later. So once you have, this is for power saving, by the way, called clock gating. So you have a path primary to ICG. I don't have a graph here, but pretend this is ICG and basically primary to the ICG cell. And you have another one called rest to memory. So basically from a flop to a memory cells. It's called rest to memory. Okay. So the benefit of having defined these groups is that you can set F level high or low. You can instruct the timing engine to work on which specific group first or a high priority. So, for example, if you have a lot of rest timing violation, you tell the engine that spend more time on this timing group versus the rest to out. So focus more on critical path, and also that each timing debugs, timing ports are going to be separate in a separate path. Okay. In a minute, you'll see this more clearly. Okay, so basically, this is a 4 timing path group, primary one, and then you have the ICG for clock gating, and you have the rest memory. Okay, so we talk about clock gating a little bit. So just briefly touch the clock gating. So clock gating technique basically is a way to shut up the portion of logic that are not used. It's a power saving technique. So traditionally they're using an AND gate, but the issue with an AND gate here is there's glitch, right? AND gate, you can see the enable here when it AND with the clock. You can see output here got a glitch. So this is an issue. So the more popular method now is they use what's called ICG cell. So usually it's composed of a latch and an AND gate like this. We'll talk more about this as we move further down in the CTS, but here I just want to introduce what's clock gating cell look like. Okay, so that's what I mean by back here by rest ICG. So basically, you have a data coming in, a queue coming in, so it comes into the input of the ICG cell, so rest ICG. So the queue output go to the enable here. So this is okay. Okay, so the time path group by default, if you don't do anything, you don't set any time path group. This is what Innova is going to give you. You give a rest to rest and then rest to clock gating cell. So basically, this is 3 groups: rest to rest, and this is rest ICG basically. And the default is everything else beside these 2. So this will be the timing. This will be the timing group default if you don't set it. So here, this example here. Here we set a different time path group. So here I set input, output into out, rest to rest, mem to rest ICC, into ICG. Okay. And then here we instruct the tool to say, okay, work on spend more time, high effort on to rest to rest to mem to rest, and oh, this is actually duplicate. But rest ICC. So these are the one that actually is going to tell the tool that spend more time on this, and then low effort on the input and output and so on. Okay. So with this granularity definition, you can tell the tool, where you want to spend the time. If you know your critical path is going to be in rest to rest, and spend more time here, and then you can lower the effort on how much time the timing engine is going to spend. Okay. And this is the default timing report, the summary. This is once you set this is what it look like here. So it breaks down per path group here. You can see, for example, if you have violation in path, you can know it's mem to rest if there's violation path here. Right now, this is 0, but if you have violent path, they'll say 1 or 4 path here. So you know this number. So you can tell exactly which path group is in. So if after placement you see that your issue is going to be in rest to rest, then you can change the effort here in the next stage. Rest to rest, put that on high, and then work on these. So if these group are met, then you can lower the effort on this specific group. So in the lab, you see today that we actually added these groups so that make it easier for us to debug timing. Okay, so in summary, if you don't set the timing path group, this is what you get. Just 3 group. But if you set it, you set your timing path group, you get a granularity of different timing path groups. So it makes it easier for the debug also to instruct the timing engine where to spend effort. Okay, so let's timing report wise, there are terminology within the tool or within industry actually. There's called WNS, it stands for worst negative slack. So in a specific timing path group, let's say reg to reg, right? This is the worst negative slack, meaning that it's the worst violation you have in this group. So there may be so in this time report here, they said there's 130 paths that violate. The worst ones is 976 picosecond. So that's called WNS. And TNS is the total negative slack, basically the sum of all of the WNS. So for example, if this is there's 130, right? And it time all the WNS, then you get this minus 19 nanosecond. Okay, so basically it's a total number. All the paths violate, all the WNS add together, you get the total negative slack. Okay, so here you can see if this is 4, so we expect these TNF to be smaller. If the number of valid path is big, then we expect the TNS to be big. Right. So this, so this is just basically the timing summary of a timing report. So here basically this is the 12,273 timing path in the design. Okay, and out of 12,000, there's 11,000 reg to reg. There's no in the out, and 245 is default, and then it's 321 input and 46 is output. So here it doesn't tell you much in terms of, is it into reg to out, or into ICC. So it doesn't have that timing path group. So it's much harder to debug or tell the tool where to spend effort versus the other one that we see here, right? So any questions on the timing path groups and why we define them?
I'm not seeing anything in the chat, and no one has used a reaction yet. Students, I will remind you, please, if well, we do have one question. What is ICG cell?
It is back to the slide. So it stands for integrated clock gating cells. So basically, it's this use in the clock path to actually it's called clock gating. It's used in the clock gating technique, right? So it's used to shut down in most of the low power design, or when you do power optimization as your target. Most of the libraries now will have this ICG cell available to use. So basically, it's shut down. You can see here this waveform, right? If you have a clock that's moving, and if you can control the enable here, right? So when the enable is high, you let the clock go through, and you get a waveform. But if you want to shut down the clock on the output here, and drive the rest of the logic here, so you would just shut off the enable, and then you shut off the clock. So whatever the logic downstream will get shut off. So it's a way of saving shutting off the portion of logic that the unused portion of logic to save power. So we're not using it. For example, you're using you have your cell phone, right? Your iPhone, and then there are you're doing texting. There's a lot of other function that you're not using, so it'll shut off the portion of the logic to save power. Otherwise, whatever you have on will continue to drain power, and then your battery go dead much quicker. So this is where to shut off the portion of the logic, like the functionality of the logic that you're not using. Okay, in the CTS portion, there'll be a little more explanation on this. Here, I just want to touch base because I introduced what's the ICG here on timing path. So that's just briefly what that is. Okay, so in pre-CTS timing op, we care about setup, right? Close setup timing, fixed setup timing. So let's briefly go over what is setup timing check. We already know what setup time is, right? You learned that. I think Phil touched it. Basically, setup time is the in a flop. There's a setup time requirements that the data must be stable before the clock edge. Right here is the setup time requirement. So the data has to be stable. It can't change. It can't change within that period of time. So this guarantees that the flop will last the correct data. So that on the output. So that's setup time and check. Setup time requirement. But what is setup time and check? So setup time and check defined basically is we talked about Slack, right? Earlier we were talking about the WNS and TNS. These are Slack, right? So this is setup Slack, works native Slack and total, right? So Slack is defined as required time minus the data arrival time. So you have a period which is the T cycle here. Okay, so in pre-CTS, there's no clock. The clock is zero. Okay, zero and no skew. So let's put that out of the way. So the clock pretty much equal to cycle time equal to required time. So required time is the clock, and then the data arrival time basically is the delay. This is the delay here plus the clock skew, but we don't have a clock skew, so we just have TPD, which is the logic requirement here, from here to here. So the delay would be clock to queue plus TPD from here to here, right? So that would be this portion plus the setup requirements. That makes sense? So this is in terms of the Slack is in terms of all these terms. Okay, does it make it a little confusing around? Let's go put some numbers to it. Okay, so see how. So let me try to figure this out. So delay here, right? The delay is T to Q plus this plus the setup time, right? So okay, so you put all together here, Slack required time, which is clock, the cycle time minus the delay, which is T clock to Q plus setup minus plus the skew, clock skew, but here T capture and launch is zero. So let's put some numbers to it in the next slide. Okay. So here is a timing report of a path. The clock period here is 4 nanoseconds. So the T cycle is 4, right? T cycle is 4. And then your delay is clock to Q here. You can see that the data arrival time here is 3 data path here is 3.847. So basically it's your clock to Q plus TPD. Here it is a pre-CS, so you have no clock delay, no latency, so it's 0, right? So this T capture is 0. So therefore the slack equal to T cycle 4 minus clock to Q. Okay, the data arrival time here is 3.87. Here data path plus the setup time requirement, which is where is the setup time requirement? Here, setup requirement here, report here, and minus 0. So you get a slack of 0.001, which is what it reported here. It's probably a little confusing at the beginning, all these numbers, but that's how this is being calculated. So based on this this waveform and this formula. So let's digest. So this is a rest-to-rest group. So later on, when we look at the timing report, you see how Innovus is report these date timing number, starting point, clock, end point. Okay. So it may not make sense to you guys right now, but later on when we play with the labs and you see the number how to calculate, it'll probably make more sense. Okay, so in timing optimization, how does the tool fix timing? So these are the 6 strategy that here that I captured to share with you guys in terms of how the tool does it. So buffering, cell sizing, VT swapping, logic restructuring, cloning, and pin swapping. So let's go over each one of these. So these are the method that, to fix setup timing, hold timing, and yeah, DRV fixing. This is a strategy that it used to fix. Okay, so buffering, what is buffering? So buffering is the process of adding buffers or inverters. Basically, it's just adding buffers in the path to either whether it's a fixed set timing or DRVs. Okay, so here example, this is it's just adding buffer, for example, here. So this logic may be a little too slow, right? Want to speed it up, it add buffers on this input here to speed up the path here. So that's buffering. So in this case, it probably speed up could be speeding up the logic, the path here. So I'm putting buffer here. So that's what is insert buffer. That's called buffering. So in the library, you can do a get live cells dot buff. You see it as different drive strength. Say there's 12x, 16x, 2x, 20x, 3 and 3x, so on. So there's more than one buffers available. Okay, and we'll talk more about why there's different drive strength later on. So this is buffering. So basically it's adding buffers inverters in the path to fix up timing or to fix DRC, max fan out, max trend, max cap. Okay, the next one is called cell sizing. So basically it's taking, it's instead of adding the buffer, it take existing inverter or buffers or any gates, is actually change this drive strength. It sizes from a 12 to a 2 or 2 to a 16, depending on what is the goal. For example, if it's want to speed up a path, this is the existing inverter 2x, right? It go in and size it, change to a 4x, so it can drive this faster, or it could be fixing DRV because the max cap issue or something like that. So that's called cell sizing. You basically swapping the cells, the smaller cell for a bigger cell of the same footprint. What I mean footprint is inverter to inverter, the same footprint. Buffer to buffer is the same footprint. Okay, so basically just changing the size and depend on the targets. So you can use the fixed timing setup and hold, fixed transition, and fixed caps by changing the cells. Okay. Cool. The next strategy is called VT swapping. VT stands for voltage threshold. So so in a given technology, usually they'll have a different VT, especially for technology that handle low power. They have been high VT, low VT, and standard VT. And for a more advanced, they have some other VT also, different type of cells. Okay, so this technique usually is not used in the really final stage of fixing setup and hold. So once you close your timing, but then you very end, you just have a few minor violations, and we don't want to touch the rest of the logic. This is what normally happens, which is we call VT swapping. So we swap a high VT to a low VT. We'll discuss what this is in the next slide, what the high VT and low VT cells is. Okay, so standard cell VT. So normally there's 3 different one, at least the low VT, a standard or regular VT, and high VT cells. So what's the difference? So low VT basically is a low voltage threshold. It is fast. Okay, so it's really built to switch fast because the threshold is small, right? Low, but if it's fast, then it's going to consume power, right? It's going to switch faster, consume more power. A regular VT is faster, is slower than the low VT, but faster than high VT. So it's kind of in between. So it's more balanced between the two. And there's the high VT cell, which is the slowest. It switches the slowest, also to use the least power. So you can see here's IVT, standard VT and low VT. You can see the power. It goes up as you go to low VT, but the delay will get slower, right? So it's opposite. So power and delay are inverse of the other. So in a critical path, to fix critical path timing, usually you have low VT, you sub it out for a high VT cell, so a lot faster, right? If you want to optimize for power, then mostly it's going to use low VT and standard VT, avoid high VT. I mean, sorry, the other way around. It's going to use low VT versus high VT because it's most power. So here example cells right here. So you have low VT cell, delay of 1 nanosecond, and power is 7 nanowatts. Standard VT delays a little more. It's slower, but it uses less power. And you have a high VT, which is a lot slower than the power is less. So this is just give you a feel of the curve, what low VT, standard VT, high VT. In a more advanced library, we'll have it's called ELVT and then SVT, HVT. So it has like two, three different more different types of VT cells. But normally we'll have 3. Okay, so this is what VT, and then different VTs cells as far as the construction of it, just different doping in the transistor that'll give you a different VT threshold. That's more of an advanced topic. So that's what VT swapping meant is used to swap high VT, low VT, and vice versa, depending on what needs to be fixed. If for power, it's swap out to high VT, and if it's for speed, swap to low VT. Okay, next one is called logic restructuring. So the tool is updating logic by changing cells or removing buffer inverters. Okay, so it can do what's called gate composition or decomposition. So this technique is use a fixed setup timing, also do some area optimization, so for reclaiming area. So this is one example of logic restructuring. So originally you have this structure of a and then it can restructure to a parallel like this, rehook it for a specific, to meet its target, right? So it can do this, the restruct logic. The functionality still remain the same. So none of this optimization technique changed functionality, right? It cannot. So it just still preserve functionality of the logic. So here you can see example of the gate composition and gate decomposition of this logic. So you have the AN1, OR1, and NOR. So it can compose to this AOI. So combine these to an AOI gate. So it compose being combined, and then it can decompose back to this. It depends on what's the target, what requirement is. So it can do either way. And here, it's just example, it's just removing buffers. So that's what logic restructuring mean, right? So just changing gates, cells, AOI to different logical reconnection. Okay, next one is called logic cloning or cloning. So it's the process of replicating logic to reduce output loading. Replicating meaning that the same logic, replicating means copy, and then produce the same logic. So here, the techniques often use the fixed setup timing max fan out. This is logic before cloning, right? Before cloning. So after cloning, what it is, it cloned this structure here and it put it on here. So here it placed it here. So it just is cloning this gate is 2/2. So that's what they call logic cloning. A lot of time, if this buffer is driving this path for, it's so slow, so they just replicate the same logic to path, and this buffer would just divide it into two fan out, and then speed up these paths. So that's a lot of time the tool does that. It happened in synthesis. It happened in place and route. I mean in P here in optimization. So this is a lot of this technique is used quite a bit in optimization, in synthesis, and in Innovus or any other PD tool. And then there's pin swapping. It's the process of swapping pin to improve timing of power. So this technique uses either to reduce power or to fix timing, right? So here's an example to reduce power. So basically here, if you see the pin C here, this is a high toggle net, right? The high toggle net, if this pin has a high input capacity, it's gonna induce a lot of power, cause a lot of power dissipation. So knowing that it's gonna move this reconnected swap to a pin C to pin A where there's low capacitance. So therefore you reduce some power. And it can do the same thing to fix the fixed timing, right? If there's this gate A to X is faster versus C is going to reroute on critical path, is going to pin swap for that particular path to go to the different gate to fix timing. Okay, so this example I just show you is to reduce power dissipation. Right, it's just swapping the pin.
Bach, we have a question that's just come in. Why is lower VT more power, more dynamic power, or leakage power? Why is lower VT more power? And then
so in a low VT, is the threshold is lower, so it's switch a lot faster. For the same logic, it's going to switch the cells going to switch a lot faster. Remember, power is a function of frequencies, right? So the faster switch is got more dynamic power, right? It's going to more dynamic powers, right? So the leakage power is on a the leakage power is not dependent on the switching, right? The leakage power is pretty much static, right? So it's really impact the dynamic power. The leakage power is wait, hold on. The leakage actually it is the leakage power. I'm sorry. Let me regroup. So, yeah, this get into the physical portion of the portion. So yeah, so basically the faster it is gonna cause that more dynamic. The leakage is let's go back to the power. Remember back in the power portion of it. Go back. Yes. So no, the high VT is going to be the least power, right? Yeah, to consume the least power, dynamic power, and the high VT is going to consume the least power. Yeah. Phil, Ting, are you guys there? I'm kind of I got a brain fart on this portion on the leakage.
Okay, so both Tian and Vu have had something come up that they are not able to attend. And students, so that you know that this is going on, Austin is experiencing a fairly major thunderstorm right now.
Yeah.
So our power is fluctuating. If we disappear, we'll be back as quickly as we can.
Yes. Thank you, Dave. Yeah. Okay. So yeah, let's we need to move through this stuff fairly fast because we need to get to the lab so that you guys can do this. Okay, so in order to do optimization we have to do some setup in Innovus. We have to tell the tool, okay, what libraries we need to use, what corners, what constraint modes, and so on, right? So for setup, we want to be in the worst delay corner, basically the max delay, the slowest library, and then the worst corner, basically the worst RC. And then, of course, we want to be in function mode. Scan mode, the timing is easy in terms of setup. Okay, so these, if in the lab you see there's an MMC definition file, these actually, all the view actually is set up in that. When we set this up, it's already set in there in that file. Okay, and then we also need to tell analysis type. So there are in three different types, or there are more than three different types, but for design, for this particular one, we're going to choose OCV, which stands for on-chip variations. And I think there is a single mode and a best and worst and an OCV mode in this libraries, in this setup. So okay, so all the views actually are already just set up whenever we define the MMC multi-mode, multi-corner. Basically, this is our timings and libraries definition, right? So, and the analysis view is already set in there at the toward end. So here's the example. This is when we create analysis view setup. So we use constraint mode default corner. And then at the end, we say, okay, the setup view is going to use this default analysis view, which is create. And then the whole will use this one. So once you open it up in the lab, it makes more sense.
Buck, we have a question that came in. Do we have any specific signs to inform us which of these methods we should choose and where we should use them? Or is it all experience-based and check timing reports with each try?
Okay, these method meaning which method? The optimization. The tool will have that actually the tool. All these available to the tool. It will use whichever it need. So you don't have to choose or anything. This is just informing you that these techniques is what we're going to use. So it happened automatically. Okay, so you just you know what's happening. So you look to the log file. Sometime it'll tell you, okay, buffering's happening or something like that. So these methods is available to tool. The tool by default will choose whichever best to meet that particular requirements. But there is some if there is, I mean, very rarely you go in and you want to limit the tools. You limit the tool, then your design will make it maybe bigger than it really need to. So you want to leave those alone and just leave the tool, let it use whatever techniques it choose that best fit. But if there is a particular path that you know upfront that you don't want this happen, well, let's say you don't want logic restructuring, it changes thing. You just want buffering, then you can go in there and limit it. Say, okay, for this particular path, I only want to do bufferings or pin swapping or whatever. So you can go in and tell a specific path, but I wouldn't do it at the beginning. You just leave it open. Let the tool use the more tools, the more method you use, the better your design going to be. Easier to meet timing, and design going to be smaller too. So let's talk a little bit about the on-chip variations, OCV. So it's a process variation occurred during fabrication of a transistor. So link width and oxide. So when you fabricate so variance can be happen to chip, or on chip. So a chip to chip, basically this is a wafer. So a chip happened here, here. The transistor side for the same location may be different, right? Maybe different here versus here. So that's what we call process variations. Okay, that's between a chip to chip, but it can happen within the die also. Okay, with this single die. So this is more problem. Start at 100 nanometer and below. Okay, so when we model, so OCV, the way we do it in the tool is we model these just become derating factors. Okay, so for time analysis, for our purpose, I mentioned there's single, there's called single. offset delay set second all set and whole and use max on uh, usually it's a common path before it's split up in two. So this is a two flop launch capture. So this is what we're talking about is the removal of these common path. So these right here, they can't the same path. You can't have two different delays basically. So, for example,
This meeting is being recorded.
path max delay late path is 3 nanoseconds, and you see the capture path here is a mini delay early check. You have what are we at? Okay, you have point okay, the mini delay is 0.8 right here. So the red number is the max delay. The mini delay is 0.8. So you have minimax. For the capture path, mini delay is 2.4, right? So without CPPR, the clock skew would be 3 minus 2.4, right? So your clock skew is 0.6, right? But for this common path until node 1, it's not realistic to have two different delays for the same path. You can't have a 0.1 here, 0.8 and a 0.1 and a 0.8 here, right? So for CPPR adjustment value, right? So you take a 1 and 1 here. You subtract the total here, so you got a 0.4. So this is the adjustment for CPR adjustment. So you take the clock skew, now you remove that. So the clock skew really is 0.2, which is the count from here to here only, right? So you get rid of this. So that's you hear the term a lot, even in the timing report. You see PPR removal, pacemaker removal, and the tool know this because this is not realistic. So it removes that. Does that make sense? Confusing enough? So the first time I've seen this, it's a little confusing, but you know, if you take time to digest this,
This meeting is being recorded.
okay, so this is just the example code of what we just talked about here. Set DB analysis type OCV. So in Innovus on the typical show, you can do a main timing analysis underscore type, and you see all the explanation of different value you can set on this analysis type. Likewise, you can do timing CPR here. So So basically here I said time analysis on CPR basically tell the tool to remove both, meaning both setup and hold, remove that path out of the time analysis because your timing will be much more accurate without it. Okay. Also no.
This meeting is being recorded.
Timing optimization engine will not use it. Will put a don't use attribute on it, and it knows not to use it in any of the buffer insertion or any of the method of the optimization. Okay. Okay, so this is just the thing I put in. Just these are just the log file from the placement run. So when it first doing timing optimizations, timing op, it will give you exactly, okay, this is the current before it does anything. This is what the WNS TNS is. You can see there are 12,073, there are 32,000 paths violated, right? And this is the worst TNS 2.9 a second, and the total negative stack of this 32,000 path, 3,200 is 12,200 nanoseconds. So it's quite big, right? And then this is the number of DRV it sees. So max caps, right? Work radius 20 nanosecond, max trend, so on. There's no max fan out, but there's max trend, max cap for this in this example. So this it gave you if you look to the log once you run your lab, you see you can see the impact what's happening, right? And you also report the density. This is the current design density before it does anything, before it insert any buffers to fix any timing or any of this. And then, so what it does is, remember, the iteration optimization is an iteration. It go through loops, runs. So 1, 2, 3 until it's actually fixed, until it's actually trying to meet timing or exhaust all the options. So it's just the log through iteration. Once you run the log, you can see all this like global optimization. So you can see here. You remember TNS was 1200 something. So after the iteration, you can see it start going down, right? So it start going down after each loop here.
Bach, we had a question come in, if you're finished with that point. How can the OCV impact on timing as it was mentioned in the pre-assessment?
Okay, let me, how can OCV impact timing? Yes, so the on-chip variations, right? So what happened, so the OCV basically is the way we model the variation on the chip. So this is the way we derate models, right? So if we don't use the correct models, our timing will be more optimistic, meaning that less accurate than the silicons will be. So OCV is just a way we model what the variation for that process is. So in a given process, there will be recommend OCV setting for that process. So, like example, you use TSMC 10 nanometer, 10 nanometer. So that process will have some guidelines. Okay, this is the OCV that value you should be setting, right? If you set the wrong value, then your timing will be off, right? Because that's the way that the tool depending on that. So it's just a way we model those things. So if we don't do OCV, we use a single worst, then the timing will be more pessimistic. Okay. So for each of the process, usually the foundry, what they do is they characterize these number, and also they do fabrication. They do a lot of this parametric testing with the modeling versus the silicon, and they'll come back and they know, okay, what's the discrepancy? How can the engineer model upfront so that the silicon will perform similar to closest much possible or on top of it. So that's what OCV is. So it's just a way we modeling the variation. So if you don't model correctly, then it will impact the timing because the derating factors are going to be different, right? The tool using different path, different value. So later on, I don't think our lab will have it doesn't have the explicit derating factors, but we only use it. There's some technology will have those numbers. I think our process is 45 nanometer. We have the value in term, but the algorithm is much more accurate versus using best and single. So we go back. Okay, so we haven't talked about hold time yet, but hold time is going to be always calculated using min delay. Your min library, the fastest library, and then setup always be the max delay. So this is a little bit more advanced topics. So when we the timing path through to an AND gate, there's going to be always a faster input, a faster into out, or A to Y or C to Y. There'll be a faster either one of those path. So the tool will know so in let's say in best and worst case, the tool always going to use max delay for all setup path and min delay for all whole path. But in OCV, the tool knows to use max delay for one path and min delay for the other path for both setup and hold, not just one. So it's a little more granularity. It's more accurate that way. Okay, this will need to explain using the diagram, but unfortunately I don't have. This is more advanced topic, but just knowing that this is if you're using this will be more pessimistic, right? Both of these, this would be more advanced. There's other method more advanced called parametric. It's called advanced OCV, and there's another one called parametric OCV, which is more accurate for more advanced node. Okay, so this topic actually is more advanced. So anyway, knowing that, yeah, so hopefully that kind of explained a little bit on why it's going to impact the timing. Okay, so once you run, so here's the timing reports for the, so you can see at the end, it's all cleaned up, right? This is setup only. And the DRV is pretty much cleaned up except the 8. This is in pre-CTS, so these 8 left over, the max cap, that's going to be on the clock nets. So it's okay at this point, it's clock nets. But after CTS, all this should be clean, but this is clock, so you can't touch it. Density overflow numbers. So in the lab, you can see what's happening here. Okay, so remember I talked about the timing path group. So here is the report timing. So once we set the timing path group, you see it break it up in each of these time report. You see it's called red to red, into out, default into ICG, different path group that we just set. So if you don't set it, it's all lumped together. So this is what if you have, look at time report, okay, if in the memory red has issue, we can go right into memory red here. So this is the detailed time report for those path group. This is the summary here, which we showed you earlier. This is summary to show you which path and so on, right? So for example, this in this slide. Red to red has a minus 2.25 WNS, right? So this is violated. So you would go into place red to reds and open this up, and you see the worst path. The first path always going to be first worst path. You can see here Slack is minus 2.2, and then and after this is the header. After this, it'll tell you exactly path by path, cell by cell, what the delay goes and so on. And we'll look at that whenever we go in the labs. Oh, okay. Here, actually, I have it here. So you can see here is the this is timing report, how to read it. So this is the header, right? This is we talked about earlier how to calculate the slack, right? Data path requirement capture here. Slack is minus 2.2, and this is the a launch clock here. This is a launch clock. It's all going to be 0, and then oops, and the other end path is the capture path. So I skip a whole bunch of thing here, but you can see it show you which cell is going through and what the timings are and so on, right? This is all 0 because this is the clock path. In pre-CS, the delays are 0. Only the data path will show timing like this, but this is the clock path. But in CTS, you would see actually delay. Why do I have this? Concurrent placement. Okay, so just design and op design, but these are two separate steps. But there is a step called concurrent placement and pre-CS together called place op design one command. Anyway, you in the lab you can play with that. I think in the lab I have a 2 separate step, but you can actually you want to play with you can instead of these 2 commands you just you run place op underscore design. And then it will does the same thing. Yeah. It's just an FYI for your information. Okay, RC extraction. So what RC extraction is the process of extracting RC for all the connects, all the wires in the design. Okay. So remember when we do a global route, right? So those RC are estimated, right? It just lay out some wires. So the RC for those nets are needed to calculate timings, right? Remember, the timing is a function of the output loading and input load. So output loadings is what the net that is driving, and the input loading of the cell of the fan out that you see. So those wires, the length of the wire, is the RC that you need to know. So so when you run a timing report or do an op, the tool first does an RC extraction automatically. So it has to figure out, what are the timing for each of those paths before it's actually go and optimize the design. So RC extraction, can be same 3 different format: DSPF, RSPF, and SPEF. The SPEF is the most popular format. Okay, these 2 not so much. So all the industry tool read SPEF. Okay, so SPEF basically is stands for standard parasitic extraction format. It's most compact and most popular. Okay, it supports pretty much all the EDA tools in IC. Okay, so it can go from one to the other, cadence, synopsis, whatever. This is standard. Okay, so why do we need it? Okay, if you normally you RC extract internally. If you save it out, you can give it to use for time analysis, simulation, and crosstalk analysis. So this is just a format, right? The interconnect, this is the RC I'm trying to show, and then this is the format. It's kind of foreign, it looks kind of strange, DNet control. So unless normally we don't go in there and look at the spec file unless there's some issue with the net, and then we can go in and dig what these are. But there is a spec manual that will tell you exactly what's happening here. These nodes, these are capacitance, these are inductance, and so on. But there is a manual to tell you exactly what these are when we need to look it up. So yeah. Just knowing RC extraction is to extract RC, and then you you can write out the spec file, which can be used for prime time analysis or simulations. Okay, so that's the point of this slide. So you can run it manually if you wanted to. Normally in Innovus, most of the tool, it will actually run internally whenever you time design or whenever you invoke the optimization engine. But you can do what if analysis and things that you can do extract RC manually, and it will actually run extraction, and then you can write out a spec file. Just use write parasitic command. You can play with this in the lab. Take a look at this slide, and you can play with this, and you can see what's happening, and you can look at the parasitic files. Okay, so that is done with this. Any question before I go to the lab? Let's see what time we got. Is it a good time? Oh, it is time for the break. So let's take a 5 minutes break, and then let me set up the lab, and then we'll go to the lab.
All right, students, we'll see you back at about 10:07.